So we talked about different components of an aircraft. I mean, here's some mathematics. Math is always appealing to engineers, right? So I just wanted to, though it looks cluttered, a lot of expressions, but just see that as, well, the basic dynamics of an aircraft. Like I mentioned before, it has 6 degrees of freedom. We represent them, the forward motion, what we call velocity. Let's start with velocity. The U, V, and W's are the velocities along X, Y, and Z axis in the body frame. I'm going to show the axes, the difference axes in the next slide. But I would like you to pay attention to this slide. So the UVWs are the velocities along the X, Y, and Z axis. The PQRs are the body rates about the X, Y, and Z axis. And terms that I would like to pay attention to. You have F sub X over M, Fx, Fy, F sub Z are the forces along the X, Y, and Z axis. So you can clearly see how thrust can contribute to a force in the X-axis, because both engines, or if you have a single engine, it's trying to generate thrust to push the aircraft forward, which is in its body X-axis. That's why when you look at the U dot equation, it's simply shown Fx equals T minus Fd, where T is the thrust generated by the aircraft, by the engine. And F sub D is a drag force. When an aircraft is going through the air, the aircraft fuselage is not an aerodynamic surface. The wings are aerodynamic, but not fuselage. So fuselage is the body of the aircraft, still offers a lot of drag. So you have to account for, your thrust should overcome the drag force. That's why the force resultant force in X-axis is nothing but the thrust, the difference between thrust and drag force. So the V and W, those are differential equations. When you see U dot, it's basically a time derivative. It's a time derivative I'm talking about. So du by dt as a function of time. So the V dot and W dots have the force components. Here I say Fy might be 0 if you are not moving, there's not a lot of force in the lateral axis. But that's not the case with the W. W has lift force. The wings are the main lifting bodies of the aircraft. They generate lift, and most of that lifting force is concentrated in the Z-axis. So you can see the thrust is mostly concentrated in the X-axis, and the lift is concentrated in the Z-axis. And now how the control gets into these equations. So just remember the F, Fy, Fx, Fz. Okay, I'm going to go over those elements in detail in the next few slides. So another thing I want to mention here is F sub X over M is nothing but acceleration in that axis. Because we don't directly measure force, we measure acceleration. Like I mentioned in the previous slide, the accelerometers set up in individual axes are meant for measuring those accelerations. And you have to derive force simply by multiplying with mass. So that's about those 6 degrees of freedom. I'm showing at the bottom of that slide kinematic equations. Though one might think the body rates, the psi theta phi, or phi theta psi, are the attitudes. Again, I'm going to show in the next slide some coordinate frames, because all these terms are vectors. Force is a vector, velocity is a vector, acceleration is a vector. So we have to, there's no escape from from not using coordinate frames. So I'll have a quick, not tutorial, but just an overview for what coordinate frames will help or come in handy for solving our problems. So here is the coordinate frames that are typically used in the aerospace industry. So the one you see on the left is an Earth-fixed inertial coordinate system. All these coordinate frames are imaginary, so you can't really draw a line, but they're reference frames. So when you're parked, when an aircraft is parked at the gate, I mean, you can imagine the gyro and accelerometers, which is nothing but the gyro is a system where it can be reset and it continuously integrates the body rates. As the aircraft moves, it has a gyro underneath, completely determines it determines the body rates in all three axes. That's the purpose of each gyro. So it knows what the aircraft is undergoing, and it keeps integrating to provide the attitudes. So you have to have a reference frame. That's where the Earth-fixed inertial coordinate system becomes instrumental. And like I said, the initial measurement unit comprising accelerometers and gyros needs that reference frame. Then for control design and for onboard electronics, you need another reference frame. That's where body coordinate system instrument, the velocities are measured, or depending on the accelerometers measure the body accelerations, while the gyros have always had the inertial frame reference, so they are doing the bookkeeping part on what the aircraft is undergoing, and then keep integrating them, and then they use the coordinate transformations, going from one coordinate frame to another coordinate frame, using the psi theta phi attitudes. It's a transformation matrix to get velocities and positions in different frames of reference. The one on the right is a northeast down coordinate system. It's again a reference frame. So when an aircraft is airborne and flying, the pilot can clearly see the north because of the instruments. So there is a northeast down reference frame that is associated with the aerospace system community. So that's more than what we need. And I'm going to skip through these, quickly glance through these slides. For nomenclature, like I said, U is the forward velocity, V lateral velocity along Y, W is the Z-axis velocity. The PQRs, remember the uppercase has some significance here. PQRs, we don't worry too much about PQRs, being lowercase or uppercase, but UVW, because U, for control engineers, lowercase u means control input. That's why we don't want to confuse uppercase U with the lowercase u. So luckily we had uppercase and lowercase. So the uppercase UVWs and PQRs represent the velocities and body rates. And then the LM, and I'm going to show in next slide, N, these are the moments, LMN, like forces, they're equivalent to forces. Forces operate along the axis, moments operate about the axis. The LM and M and N are the moments about the axis. And M is a dynamic mass. M is a term generally used to represent dynamic mass. When an aircraft is flying, dynamic mass remains almost constant except for the fuel depleted as you're flying from point A to point B. If somebody would like to take the change in mass, that's ideal. If not, since you have a man in the loop, the pilot can handle that. or the control system can handle that. G stands for the gravitational field strength. That's what it goes by. T stands for engine thrust. And we talked about psi theta phi or phi theta psi. Those are the attitudes. And the psi theta phi are nothing but how far away the body axis has rotated from the inertial frame. We have seen the inertial frame and body frame in the previous slide. So the difference, so the gyros and the kinematic equations kind of keep track of those attitudes throughout the flight. Continuing on, I think we have gone over these. F sub D stands for drag force, FL is the lift force, Fx, Fy, Fz, we talked about it. The Ax, Ay, Az's are the accelerations. And here is a supplementary set. Again, I don't want to spend too much time on it, but just for completeness, what these forces and moments are made of. If somebody would like to know, the forces and moments are made of a half rho Vt square like term, which is a dynamic pressure Q bar, times the surface area. Drag force is based on the surface area of the fuselage. And the CD, C sub T, that's an aerodynamic coefficient. I have a slide to talk about the aerodynamic coefficient, the CD, CL, C lowercase l, C lowercase m, C lowercase n. So that make those, we're talking about FDs and FLs, the drag force and lifting force, and the L, M, and N, those are the moments. So these 5 forces and moments have corresponding aerodynamic coefficients. It's worth a slide to talk about those, where people get those coefficients from. And we have seen W's and V's. There is a V sub T, which is total velocity. There's a typo, it's a Vt square, should be U square plus V square plus W square with no square root. I forgot to remove the square root. Or V sub T without square is U square V square W square under the root. There is another term that's very popular in the aerospace community, which is Mach number. How people get Mach number. What they mean by Mach number is essentially, it gives you a feel for the speed of the aircraft. It's a non-dimensional number. The reason being, it's trying to, the way it is shown here, it's computing the total velocity of the aircraft, or it's derived from the total velocity of the aircraft by the speed of sound, which is another speed, at that altitude. So there is an international standard atmosphere given the altitude to generate the air density at that altitude and speed of sound. So once you know the speed of sound, you can compute the Mach number knowing your own aircraft velocity. You have air data sensor on board to provide that information. Q bar, as I mentioned before, is half rho Vt square. And one thing I want to mention here, while we are still on this slide, the C, D, the C's, those are the aerodynamic coefficients. Depending on what that coefficient stands for, they could be functions of total velocity, like the way it is shown here. The drag coefficient is a function of total velocity. The lift coefficient is strictly a function of angle of attack. And angle of attack, as you can see on the left, defined as arctan W over U. W and U are the forward, W is the normal velocity in the z-axis. U is the forward velocity in x-axis. So the CL, aerodynamic coefficient, is a function of alpha. The lowercase LMN, the CL, CM, CN coefficients are functions of angle of attack, and the beta is angle of side slip. When the aircraft moves sideways, there's an angle of side slip that you can, or it comes about. So the coefficients are functions of angle of attack, angle of side slip, and Mach number. And depending on which moment you're talking about, if it's a rolling moment, it's a function of aileron deflection. If it's a pitching moment, it's a function of elevator deflection. And if it's a yawing moment, it's a function of rudder deflection. So I did mention about the aerodynamic coefficients. So how would one obtain the aerodynamic coefficients? Though we're talking about control design, I still wanted to touch upon the aerodynamic coefficients, how one would get them. So, I mean, it looks like we have already hit the 48 minutes mark. I'll try to speed up, but this slide is worth taking the time. So the aerospace industry has typically taken an aircraft, conceptual aircraft, and has come up with a scaled down model that they would test or evaluate in a wind tunnel. A wind tunnel is a tubular structure, often narrower in the middle, and then that's where the test article, the scaled down model, will be kept, and they run the test. They run the test to determine these coefficients because CMC and CL, they are functions of ailerons, elevators, and rudder. So they deflect them in the wind tunnel to determine these coefficients. Once these coefficients are determined, they will be non-dimensionalized because certain area of aileron with a surface area is contributing this much, causing this much aerodynamic force, or contributing to this much aerodynamic force. So what a real aircraft scaled up or one-to-one model can generate. So once they have these non-dimensionalized coefficients, they can scale them up using appropriate surface areas and moment turbulence. So that pretty much covered the tool chain, and we covered the tool chain and aircraft. How involved it is to model an aircraft. So the third segment of this presentation webinar is how one would go about designing a autopilot. So any design would need requirements. I mean, we are all familiar with requirements, right? So a top level, a very high level requirement for an autopilot would be something like aircraft shall follow a given heading and hold a cruise altitude. So when aircrafts are flying from point A to point B, they are given by the air traffic controller a heading and altitude. They want to separate aircrafts in the altitude. They give them they specify an altitude. They want a separation distance between aircrafts flying in parallel, close to each other to avoid any collision. So a top level autopilot design, you could have a requirement like this, a heading, specified heading, and cruise altitude. And heading, I see there's a picture to the right, shows heading as the angle between the local north in northeast down reference frame, and the velocity vector. We talked about total velocity. And if you were to project the total velocity into the XY plane, the body XY plane of the aircraft, you get a velocity vector projection. And the angle between the local north and that projection of the velocity vector is called heading, because you have to go in one direction from one city to another city. So those are the two requirements. And how one would go about using the V model for designing. The software development methodology using V model has a verification segment. So you take the requirements and then you break it down into multiple requirements. Just autopilot design does not mean anything. So you have to specify an aircraft you have to specify a sensor suite, you have to specify an actuator, and then you should talk about the autopilot. So when you say the system requirements could be autopilot, but you have to break it down into what all you would need to be able to design that autopilot. The subsystem requirements could be the aircraft, sensors, and actuators. And then, when you have subsystems, you have units within the subsystems. You have to have requirements. I mean, today's industry, you don't have one company building the entire aircraft. Or same thing holds good with the automotive industry. So you have to give out your requirements to individual manufacturers. Like sensors are manufactured by one company, actuators are manufactured by another company. So you give away those requirements to individual companies to build their components. And you, as a manufacturer, if you're a Boeing or someone like Boeing, so you would take all those models and test them in an integration test. Some are models, some are real pieces of hardware, so on and so forth. So that's the verification part, where you would take it through the design phase. And then on the validation, again, like I said, today all controllers are implemented in as electronic control units. So there is a software element that's running on the hardware. So there's no guarantee that if something had worked in the design, that it would work in reality when it's then faced with other hardware, that it would work. So you have to take it through the validation stage. That's what the V model essentially is all about. So time-wise, I think I need to speed up. So model-based system design, how all these aspects can be covered in Matlab Simulink. One could have a very top level. This is a Simulink model that I have built just for the purpose of the webinar. Most of them are skeletal, except for the 6DOF model to the right that has some meat in it. The Turbofan engine system, these are part of Simulink block set. You can drag and drop them, basically. I have just identified the autopilot over here. And the dynamics part of the aircraft that we have gone over comprises, is modeled from atmosphere. The altitude going in, generating the Mach number, so on and so forth, speed of sound, etc. And those outputs going through the aerodynamic coefficient, generating the aerodynamic coefficients, and the coefficients are fed to the forces and moments block to generate forces and moments. The forces and moments go into the equations of motion to generate accelerations and body rates. And those accelerations and body rates are fed back to the controller to design the control law. So I will, like I said, this is the unmasked version of the 6 degrees of freedom. Whatever you have seen in the equations, nonlinear differential equation, they're captured using Simulink blocks. And then here is a quick engine, turbofan engine model, which has a lot of lookup tables. An altitude goes in, and then thrust comes out of these models. Also, the engine model needs a Mach number. So these lookup tables are manufacturer specific. General Electric makes aircraft engines, so they come up with these lookup tables to support the integration test. So I'm trying to capture the atmosphere model as built in Simulink. Only the bottom block that I'm pointing here is the atmosphere model. The rest of them are just algebraic equations. So here is a controller and estimator system. which makes the autopilot. Why we need an estimator? We need an estimator because the measurements that the accelerometers and gyros provide are not sufficient to design a control law. So you have measurements. From measurements, you have to estimate the state. The state happens to be, for an aircraft, the state is nothing but the velocities, the UVWs and the PQRs. So you need an estimator. I'm showing in the next slides, what it would take to design a controller and estimator in Matlab Simulink environment. It's just the same Simulink model, in a different orientation, different graphic, just to show where the controllers, the signal flow, basically, what goes where. This block diagram shows the signal flow. So the underlying algorithm for the controller and designer is, the tools are provided. So once you have a model, once you build a model in Matlab Simulink, you can design a control law and an estimator with that information. All you have to do is you have to extract a bunch of linear models at different operating points and use those linear models to design controllers or gain matrices at those operating points. And Matlab has solvers for those. I just have these just for completeness. So there is a minimization going on here. Controller and estimator, they define a cost function, which looks more like a quadratic function. And any quadratic function can have a minimum when the derivative is 0. So that's what is going on here in the equations. So you find a gain matrix K. Similarly, you find an L gain matrix for the estimator, and you put them all together. You simulate, that is the downward V I have shown before. And then I'm not touching on the upward V because it involves code. But Matlab Simulink provides a real-time workshop, which is used for code generation. So one could replace the modeling blocks with equivalent code blocks and evaluate the controller and estimator designs to see how well they perform when the code is in the loop. So that completes kind of the V model. So this is how I want to conclude my webinar. So what is in it for me? Ultimately, everybody would ask himself or herself. So having this knowledge of Matlab, Simulink, the design knowledge, you're all engineers going to be working for different companies. So you may be asked to, the first question they may ask is whether you are familiar with Matlab Simulink and to what degree. So if you have the knowledge of Matlab and Simulink, what its capabilities are, it would help a great deal. So the Matlab Simulink toolchain can be used for modeling and simulation and code generation. That's what I'm trying to show here. The conceptual design, the proof of concept, can be done quickly for both aerospace, automotive, and power engineering. You can also do rapid prototyping and test with pieces of code in hardware, pieces of code implemented in software, and some could be Matlab functions. Matlab has a compiler which could take a function, Matlab function, and generate code for speeding up the computation, basically. As you know, Matlab is an interpreter-based language. That's what I meant by hardware in the loop. So you could have a combination, mix and match. In an integration test, you're slowly transitioning from completely modeled, like a desktop application to a lab environment. So you can transition and progress in that direction, one piece at a time. So that's end of the webinar.